Okay, so we'll be looking at renal function and then some renal pathologies. Okay, so we are already assuming that we all know the parts of the nephron, and we have some basic idea of renal physiology. Okay, so that's the assumption that we are making over here. Okay, good. So I'll just emphasize some things, then we move on to the chemical pathology aspects. So the first principle I want to point out is that the kidneys receive about 22. The kidneys receive about 20 to 25% of the renal of the cardiac output. Okay, so if the cardiac output is about 5 liters per minute, and let's assume that the kidneys are receiving, let's even say 20% of it. Okay, that means that the kidneys are receiving like 1 liter of blood every minute. So every minute, 1 liter of blood will pass through the kidneys. Now, for most organs, okay, for most organs, blood supply is just for nutritional. Blood supply is just for nutrition. Okay, it's just for nutrition. But when it comes to the heart, when we come to the kidneys, blood supply to the kidney is not only for nutrition, okay, but it's also for filtration and excretory purposes. That's the reason why the kidneys, though it weighs about 0.4% of the entire mass of the person, okay, is receiving 20 to 25% of the cardiac output. Okay, and the reason why it's receiving this large amount of blood is not because of nutritional purposes, but because of the excretory function of the kidneys. Good. Now, the functional unit of the kidney is the nephron, okay? And we know the nephron has several parts. Okay, we have the glomerulus, and we have the Boltzmann's capsules, we have the proximal convoluted tubule. Okay, then we have the loop of Henle. Okay, the descending loop and then the ascending loop. Okay, then we have the distal convoluted tubule. Then you have the collecting tubules and then the collecting ducts. Okay, so these are the parts of the nephron. And then I'm sure we know the functions of each of these parts. So each part of the nephron performs a specific function. Okay, the glomerulus is responsible for ultrafiltration. Okay, then the proximal convoluted tubule is responsible for reabsorption of most of the filtered electrolytes. That's the function of the proximal convoluted tubule. Its function is for reabsorption of most of the electrolytes as well as most of the filtered nutrients. Okay, so if let's assume proteins have been filtered, the proximal convoluted tubule will reabsorb those amino acids. It will reabsorb glucose, it will reabsorb sodium and other electrolytes, okay, bicarbonate and other electrolytes. So that's the main function of the proximal convoluted tubule. Now, the function of the loop of Henle, okay, is for creating what is called a concentration gradient, okay? So it ensures that the medulla of the kidneys, for the kidneys, we have the cortex and we have the medulla, okay? The function of the loop of Henle is to concentrate the medulla. If the medulla is concentrated, then you can either concentrate or dilute the urine. Okay, so that's the function of the loop of Henle. Okay, we have the descending and ascending. You can even talk about the thin descending, thick descending, thick ascending, thick descending, all those things. Okay. And then we know the function of the distal convoluted tube. The function of the distal convoluted tube is also for reabsorption of electrolyte and water. Okay, but in this case, the reabsorption is dependent on hormones. That's the reason why for sodium to be reabsorbed at this part, you need aldosterone. Okay, so the reabsorption of sodium and water, okay, from the distal convoluted tube into the collecting duct, okay, is dependent on hormones. Okay, good. When we get to the collecting duct, it's also for reabsorption of water, and this time is dependent on ADH. Okay. So basically, these are the parts of the nephron, and these are the functions of the nephron. Now let's go to the functions of the kidney itself. When you talk about the kidney, what are the functions of the kidneys? Because the kidneys are very important structures. Okay, if you understand the functions of the kidneys, then you can tell us what will happen to someone with renal failure. Because when you say failure of an organ, it means the organ is not performing its function. Okay, so that means that you first must know the function of the organ. So when you take the kidneys, okay, when you take the kidneys, please, is the slide clear enough? It's very faint. I don't know whether you guys can see it. Please, is it clear enough?
No. Yeah.
Yes, it's clear.
Okay, good. So the first function of the kidney is for water, electrolytes, osmolality, acid-base regulation. If you remember from the previous lectures, okay, the tutorial I gave you guys, I took you guys through how the kidneys are able to regulate water, are able to regulate electrolytes, and even the osmolality and an acid base. Okay, we looked at all those parts. So that's a very important function of the kidney. Then the second function of the kidney is for excretion of waste products. Okay, so most of the waste products are excreted by the kidneys. Okay, and also for excretion of drugs and their metabolites. So the kidney is also an endocrine organ. It's an endocrine organ. And its function as an endocrine organ is to produce the hormone erythropoietin, okay? And erythropoietin is a hormone which stimulates hematopoiesis, okay? And just to add this, remember that the strongest or the most potent stimuli for erythropoietin production is hypoxia. Okay, so hypoxia is a very strong stimulus for erythropoietin production. Okay, so we've seen erythropoietin. We also know that the kidney also produce or it activates vitamin D. And this is a very important function, okay, activation of vitamin D. And we know that activated vitamin D, okay, aids in calcium reabsorption. Okay, that's why it's called calcitriol, okay. It's for calcium metabolism, calcium absorption and regulation. Okay, and then the next thing the kidney produces is renin. We know renin. Okay, renin in itself it's not a hormone. Okay, it's an enzyme. It's an enzyme, but people classify it as hormone. So remember that. Good. So we know the function of renin in the renin-angiotensin-aldosterone function. Okay, good. Good. Now let's look at I mean, the priorities of the kidneys, okay, in its renal function, it has certain priorities, okay. So the first one is to maintain blood volume. So that's the most important priority of the kidney. And it does this by reabsorbing water, okay, at the renal tubules, okay. Then the second one is maintenance of electrolyte composition. Then the third one is osmolality, and the fourth one is acid-base balance. This is the priority, okay. So it's orderly. Kindly note that, okay. I'm sure we all know the anatomy and then the histology of the kidney, so I'm not going to spend much time over there. Good. Now we can look at the kidney as, or sorry, when you take the nephron, we can divide the nephron into three parts, okay, three parts basically. We have the glomerulus, okay, then we have the tubules, then we have the interstitium. So the interstitium is the parts, okay, of the kidneys which surround the nephrons. So all the areas surrounding the nephrons, okay, we call them interstitium, okay, and they contain a lot of blood vessels. So we can group the kidney into, or we can classify, sorry, the nephron into three parts, okay. But physiologically, we only look at the nephrons. We look at the nephrons by looking at the glomerulus and then the tubules, okay. So if you want to find out whether a nephron is effectively functioning, okay, we have to look at the glomerulus function as well as the function of the tubules. Okay, so we are going to look at the function. How do we know whether the glomerulus is working very well? And how do you know whether the tubules are working very well? Okay, so the first thing you're going to look for is the test for glomerular function. In order to understand the test for glomerular function, there is a certain concept we call the glomerular filtration rate, which must be understood. Okay, now when you talk about the GRF, which is the glomerular filtration rate, what are we talking about? Now, I've already emphasized that the kidneys receive 20%, 25% of the cardiac output, okay, which is about 1 to 2 liters of blood in a minute. Now, all this blood is coming to the kidneys, okay, and this blood coming to the kidneys within the minutes, part of this blood is going to be filtered. Okay, not all of that blood coming into the kidney in 1 minute to be filtered. Okay, so the glomerular filtration rate is giving us an idea, okay, of how much of the blood is being filtered. Okay, it's just giving us an idea how much of the plasma is being filtered by the glomerulus. Okay, so that's the whole concept. Okay, and we say that the glomerular filtration rate is 120 mL per minutes. Okay, 120 mL per minute. So that means that in a minute, only 120 mL of fluid is filtered by the glomerulus. So when you say glomerulus, okay, when you say the glomerular filtration rate is 120 mL per minute, what we are saying is that in 1 minute, okay, the glomerulus filters only 120 mL of blood. So now you can imagine that 1 liter of blood is coming to the kidneys, okay? Now this blood which is coming to the kidneys, we want to filter the plasma components, okay? So you are looking at the plasma components. So with this plasma component, we are saying that only 120 mL of the plasma is filtered in a minute. Okay, so that's the concept of glomerular filtration rate. Okay, now let me bring about the concept of clearance. Okay, so let's assume that someone takes in a certain drug. Okay, someone takes in a certain drug. We know that the kidneys, let's assume the kidneys are the only organs that can excrete this drug. Okay, so when you talk about clearance, all that we are saying is that how much of the blood has been cleared of this drug, okay, in a given time. Okay, so the clearance means that how much of the drug has been cleared from your system within a given time. That's the concept of clearance. Okay, so now the reason I'm bringing up this concept of clearance is because we use the concept of the clearance to calculate the glomerular filtration rates. Okay, so now let me give you an example. Let me use this to explain. Let's assume that, okay, let's assume that you injected a certain drug to a patient, okay? Then you collected the patient's urine for 24 hours. So you inject the patient with the drug, okay? Then after 24 hours, you collect all the urine that the patient will urinate, okay? You gather all of them. Okay, then the next thing you do is that find the concentration of the drug in the urine. Okay, then you also find the concentration of the the concentration of the drug left in the patient's system. Okay, so this is what we are going to do. So let me read this part for you. Consider any plasma constituents, or let's assume any drug, okay, and that drug is or can be passed into the urine. Okay, so if you want to know the exact amount of drug that has been passed into the urine, okay, just multiply the urinary concentration, which is U, times the volume that you collected within that period of hour. Because remember that from SHS, we know concentration is equal to mass over volume, okay? Therefore, mass is equal to concentration times volume. So if I multiply the concentration of the drug in the urine, okay, by the volume of urine, then I'll get the amount of the drug that is excreted. Okay, so that's where this equation is coming from. Good. Now, the principle is this: the amount of drug you injected into the person must be equal to the amount of drug which comes out into the urine. Okay, so then how do I get the amount of blood, or sorry, the amount of drug? Okay, so in order to get the amount of drug, okay, as we said, the amount of drug in the urine is going to be the concentration of the urine times the volume of the urine, okay? Good. That should also be equal to the concentration of the drug inside the person times the volume of distribution, okay? So the volume of distribution, which we talked about earlier on, okay, times the plasma concentration. The P over here is the plasma concentration, okay? That's the plasma concentration. So the volume of plasma times plasma concentration should give us this amount, which is the U, which is the concentration of the drug in the urine times the volume, okay? So if I want to get the volume, I'm just going to divide it by this P, which is the plasma concentration. Okay, that's going to give me this volume of plasma. So we are saying that this volume of plasma has been cleared, okay, of the drug. this is the formula for clearance. So the formula for clearance is equal to concentration of the drug in the urine times the volume of urine collected in 24 hours, all divided by the plasma concentration of that substance. Okay, that will give us the volume of plasma which has been cleared of the drug within that time you are talking about. So let's assume I got the volume to be 3 liters. Okay, that means that within 24 hours, okay, the drug has been cleared from 3 liters of the plasma. Okay, that is the concept of clearance. Good. Please, is it clear? Any questions so far? Okay, I'm sure we all understand.
Mine's please, it's not clear.
It's not clear. Okay, then let me go over it again. So this one is just like C1V1 is equal to C2V2. Okay, we know that formula from SHS. That's C1V1 is equal to C2V2. Okay, concentration. So the C1 is, let's assume C1 is concentration of the drug in the plasma. Okay, and then the V1 is the volume of the plasma. Should be equal to C2V2, where C2 is the concentration of the drug in the urine times the volume of the drug in the urine. Okay, let me give you an example. Okay, let me give you an example. Let's use this example to analyze what you've been saying so far. Okay, let me see. Can someone read this question for us? Who wants to read? Okay, there's someone called Abena Odame. Please read this question for us.
A male of 35 presenting with groin pain has 150 micromoles per liter of 2,160 ml is collected and found to have a creatinine concentration of 7.5 millimoles per liter. A. Calculate the creatinine clearance and comment on the result.
Okay, good.
An error in the...
It's okay. Thank you very much. So,
Okay.
so you see, this is what is done on the word. Okay, so we are calculating the clearance of creatinine. The reason why we are calculating that is that is going to give us an idea of the GFR. Okay, so in measuring GFR, we use the creatinine. Okay, in human beings, I'll explain it down. Okay, so what's going to happen is that you measure the person's serum creatinine level, and here we are getting something like 150. Okay, then look at the time over this 24 hours. So within 24 hours, you allow the person to urinate, okay, or you collect all the urine within 24 hours. And then this was the volume you got, 2,160 ml. Okay, then the urine that you collect, okay, you calculate the creatinine concentration in the urine. So you note over here that here we calculated the creatinine concentration in the plasma or in the serum. Okay, we got 150 micromoles per liter. Good. Then you took all the urine sample in 24 hours, and this was the volume 2,160 ml. And then the concentration is 7.5 millimoles per liter. Okay, good. So now with this is the volume, this is the concentration. If I multiply this volume by this concentration, I'll get the amounts of creatinine. Okay, so then what do I do? first of all, make sure that the units are the same. Okay, so I can convert this to liters. So that will give me 2.16 liters. Okay, this part 2.16 liters. Okay, and if I multiply it by this 7.5, okay, whatever answer that I will get, okay, will be in millimoles. Okay, good, will be in millimoles. Good. Then when I'm done with this part, with the urine part, then I come to the serum. With the serum, I notice that the serum concentration was 150 micromole per liter. Okay. So with this, let's make sure that the units are the same. So we convert this to millimoles. Okay. So you can multiply this by 10 to the power 10 to the power 3. Okay. Good. So then with this volume times this concentration, I would divide it by this 150. Okay. And whatever value that I get is equal to the creatinine clearance. Okay. But you see, what I've done is even not the exact way. Okay, but that's the general principle. Okay, I'll show you how to exactly work it. Okay, so always multiply the urine, okay, volume by the urine concentration, then divide by the plasma concentration. Okay, and that will give you the clearance. Okay, what I've said so far it's not how it's done. Okay, but it's just going to give you an idea of how it's done. Okay, so what you should do exactly is to get the urine flow. So we are using the term urine flow rates, not urine volume. So in order to get the urine flow rate, okay, what you do is the urine flow rate means that is the amount of urine divided by the time, okay, which is 24 hours. Okay, so let's go over here. So what they are doing in the solution is that they are ensuring that the units are the same. Okay, so they are converting this 7 point. They are converting all of them to micromole. So here, they are multiplying this by 10 to the power 3. Okay. So when you do that, you are going to get the urine concentration to be 7,500 micromole per liter. Okay, good. Then, as I said, as I said, what we are calculating next is the urine flow. Okay, and when you talk about urine flow, we mean that how much the volume that we've collected, okay, divided by the total time. Now we collected 2,160 mL, okay, and the unit is mL per minute, okay. So 2,160 in 24 hours. So if I divide it by 24 hours, okay, whatever answer I'll get will be in mL per hours, okay, but we want to convert it to mL per minute. So you multiply this 24 by 60, okay, that's converting the 24 hours into minutes, which is 1440. So if I divide the 2,160 by 1440, I'll get 1.5 mL per minute. This value over here is what is called the urine flow rate. Good. So we have 1.5 mL per minute, which is the urine flow rate. Now, after getting this urine flow rate, okay, after getting it, what I'm going to do is that then I just multiply it by the 1.5, then I divide it by 150. Okay, that will give me the creatinine clearance. Okay. So please, the session is ending. Okay, so let's quickly join early so that we can continue. So I'll go over this again. Okay, I'll go over this again.